This lesson deals with Supplemental Problem 3.8. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 9. In Chapter 3, we developed a piecewise linear model for the transistor by linearizing the VI characteristics of the transistor. Let's go back and take a look at that. That's in the Chapter 3 lecture notes on page 16. And by doing this, we're able to come up with a set of linear models that were pretty easy to work with. We focused on this first quadrant and the characteristics of the base emitter diode. Because this is an NPN transistor, we can forward bias this junction and reverse bias this one. That's what's called an inverse active region. The base collector being forward biased and the base emitter being reverse biased puts us in this region over here. And we can again call this an active region, although we're going to call it the inverse active region. As the set of curves very similar to the first quadrant, we'll see if the ratio of some of the currents is a different value. We also had in this quadrant from our Ebers-Moll model, we had this relationship that the ratio of minus I sub B to I sub B was beta R. And we showed with some algebra, because the emitter is not shown on here, that the collector current is the negative of the quantity beta R plus 1 times I sub B. Let's see all the things that are true when we're operating over here and operating over here. Well, first of all, the voltage across the base collector is going to be a constant. I'm going to call that V sub BCR on. And the current in here is greater than or equal to 0. If we're operating in this set of curves, then we're less than or equal to this saturation voltage I'm going to call V sub CER sat. And the collector current is less than or equal to 0. Then we also had this Ebers-Moll relationship for the ratios of currents. Let's go back to page 9. Those are all the conditions I had here. And this is again when we're operating under the conditions of forward biasing the base collector diode and reverse biasing the base emitter diode. That's just the opposite of what we did in the first quadrant. What we're doing here is really just interchanging the collector and the emitter. If you look at all these conditions, they're really the same we did in the first quadrant, where I'm going to call this now the new collector and this the new emitter. Can we build all these conditions into the model? Clearly this is a battery between the base and the collector. I've got a battery, I'll call it V sub BCR on. And then I've got a relationship between the current in the emitter and the base. I could use a current-controlled current source. Here's my emitter current, base current, and collector current, just taking our original definitions. And this current is the negative of beta RIB, so I'll show my current source going in this direction. Clearly, we don't have all the things covered here. We've got this one covered and this one covered, but we don't have these other ones covered. If I assume that this is the correct state of the transistor, then I'll put the model in and begin to analyze the circuit, and I need to check a few things. Current in here can be positive or negative. I need to check that that's greater than or equal to 0. Also, the voltage across here can be positive or negative, so I need to check that that's less than or equal to V sub CER sat. About the collector current. If the base current is greater than or equal to 0, let's see if that implies this by going back and looking at that set of equations in Chapter 3. This relationship here. I sub B is greater than 0, then I sub C, so it'll be less than 0. That other condition here is actually satisfied by having this relationship and this relationship satisfied. Put the model in. We'll need again to check that I sub B is greater than or equal to 0 and that VCE is less than or equal to VCR sat. What about the PNP transistor? Well, everything's the same. Normally we draw the PNP transistor with the emitter on the top, and now it's going to become our new collector and our new emitter. I'm going to follow the original notation of the base collector and the emitter. All this stuff here is the same. Just simply going to change the subscript. We're going to change the direction of all the currents. Base current's coming out, the emitter current's coming in, and the collector current's going out. And all the conditions turn out the same. Put that model in, and we'll need to check that the base current is greater than or equal to 0, because we already reversed the direction of that. The emitter collector voltage is less than or equal to the emitter collector reverse saturation voltage. Let's do an example. Given this one transistor circuit with an NPN transistor, two 1K resistors, and two batteries, could you find the current I and the voltage V if the base collector reverse turn-on voltage is 0.72 and the collector emitter reverse saturation voltage is minus 0.02 and beta R is equal to 4? These are very different numbers than we had from the first quadrant for an NPN transistor. I'd like you to assume that you're in the inverse active region and then check that assumption. The first step is to replace the transistor by its assumed model. Between the base and the collector, I have a voltage now of 0.72, and between the emitter and the collector, I have a current source of 4 times I sub B. I've got to solve for IB and V sub CE. Let's go around the loop this way. The rise in voltage is 5. The drop is equal to IB times 1K plus 0.72 And then the current in this resistor going in this direction is going to be I sub B and 4 I sub B, 5 I sub B times 1K. 5 volts minus 0.72 over here, and then divided by, here's 5K and 1K, so 6K. That gives me 713 microamps. Collector current here in the opposite direction is going to be 5 times I sub B, but with a minus sign, so minus 5 IB. 5 times that is 3.565 milliamps. I want to solve for the collector emitter voltage. It's going to be this node voltage minus this node voltage. This node voltage here is going to be with the direction of I sub C in this direction. It's going to be a minus I sub C times 1K. And then this node voltage is 4.5, but we're going to subtract that, so minus 4.5. Substitute in for I sub C a minus 3.565 milliamps, so the two minus signs cancel. The difference of these two is minus 935 millivolts. The base current is greater than or equal to 0, and the collector emitter voltage is less than or equal to V sub CER sat. The assumption checks. We can now proceed and solve the rest of the problem. The current I is equal to the current IB, it's this current right here, and that was equal to 713 microamps, and the voltage V is going to be equal to the drop across this resistor, which is going to be minus I sub C times 1K. Putting in a minus value here, we get a plus, and the product of those two is 3.565 volts. And this is supplemental problem 3.8.